So in this new playlist, I'm going to be talking about an important topic, contrastive networks, and also siamese network. All of these are just part of deep metric learning, a kind of an approach to deep metric learning. So we should know about contrastive laws, triplet laws, because sometimes we have just an anchor here and we have these positive and negative elements. And sometimes we had even more than three, it's quadruple laws, but it's rarely used. This one is rarely used. The other one, structured laws. So I consider it in the category of structured prediction, which is a huge topic. Another one is n-pair laws, or magnet laws, clustering laws, mixed laws. So it's important to note that the hard negative is when the distance between your anchor point, this anchor point, and your negative is less than distance between that anchor point and positive. So this is very bad, so it's very strong, so it's hard negative. And then we can weaken that, so semi-hard and easy negative mining. But self-supervised learning methods some of them are contrastive learning. But there are some non-contrastive approaches, also I will explain in this playlist, that rely only on positive samples from the data, such as the approach of BYOL or SimSiam, which are, for example, this one is very popular in Google and Microsoft. And so there's a paradigm shift between deep learning and contrastive. So we have a small data set, but in contrastive self-supervised learning, we have large data set. And so I asked ChatGPT about the difference between contrastive network and siamese network. And it said that in siamese network consists of two identical subnetworks that share the same architecture and weights. But contrastive network typically consists of single network that takes two input samples directly. I mean, we do augmentation, both in computer vision and natural language processing. And the network produces embedding for each input. And for training objective for siamese network are trained using siamese or one-shot learning, but the contrastive network are trained using a contrastive learning objective. So pairs of positive examples or negative examples, and they are used during training. There are some use cases for siamese network that are commonly used for tasks such as face recognition, signature verification, but in the contrastive world, they have gained popularity they started from self-supervised learning and unsupervised learning representation tasks. So siamese use twin networks to learn similarity, while contrastive network using a single network computes similarity or dissimilarity. Because we have one image, for example, we do augmentation, and we have different views. But it's more than that. I mean, the answer of this ChatGPT is quite naive and it has many problems. So let's focus on this paper in 2022, which is siamese prototypical. So it uses these prototypes, and so it was once, I think they draw inspiration from that few-shot learning prototype network or proto network that I've explained in playlist for few-shot learning. And these are positive samples. They are very related to this article. So contrastive self-supervised learning is a practical solution that learns meaningful visual representation from massive data in an unsupervised approach. The ordinary CSL embeds the feature extracted from neural networks onto specific topological structures. One of the drawbacks of this self-supervised learning is that the last term requires a large number of negative samples to provide a better mutual information-bound ideal. However, increasing the number of negative samples by larger running batch size also enhances the effects of false negatives. Semantically similar samples are pushed apart from the anchor point, hence downgrading downstream performance. So they tackle this problem by introducing a simple but effective contrastive learning. The key insight is to employ siamese-style metric loss to match intra-prototype features while increasing the distance between inter-prototype features. It is demonstrated that the loss, which requires a large number of negative samples to provide better mutual information, which leads to large batch sizes. Although the growth of computation resources nowadays can support training with batch sizes of dozens of thousands, the large mini-batch often results in new trouble. The chance of semantically similar samples being computed as negative ones is raised. So one straightforward approach to address is to employ label information of samples explicitly that we use supervised contrastive learning, like the siamese LSTM or sentence bird in 2019 by Mrs. Grevich in Darmstadt, I think. So the samples are regularized to corresponding semantic clusters with an ordinary cross-entropy loss. The obvious shortcomings of this approach is the prerequisite of downstream task knowledge. Another approach is to use prototype to tackle the issue in a task-agnostic manner. The term prototype refers to clusters, the samples in the embedding space. So the clusters can be either predefined or computed during training mini-batches. The samples from the sample prototype contain highly similar semantic information. So the goal is to learn meaningful visual representation in an unsupervised and task-agnostic style. To achieve this, we present a simple but effective variant of contrastive self-supervised learning. The fundamental idea of this method is to group the samples in the embedding space to produce prototypes. Then we refine prototypes by maximizing or minimizing the inter or intra-cluster distance between the samples. Finally, we regularize views of samples using prototypical information with cross-entropy. So this is the illustration of siamese prototypical contrastive learning. The embedded features are grouped into separate prototypes, and a siamese-style metric loss is employed to match intra-prototype while pushing apart inter-prototype features. Because if you work with prototypes, these clusters, then it is robust. It is less prone to noise. So that's why it's so logical. Even the proto network in few-shot learning uses this idea. So via your input, you have a number of prototypes, set of augmentations, and then we initialize, then obtain the cluster. First, we obtain the clusters, just using, for example, k-means clustering. Now, once we get the prototypes, then, for example, these clusters, we sample X from the corresponding clusters. And after that, we obtain these representations from inputs and their augmented views. And then we compute the loss of contrastive loss, metric loss, and prototype loss. And so the first step is to group the embedded features into separate clusters in an unsupervised manner. And during the feature extracting phase, we first draw an anchor prototype and a sample mini-batch. Then we draw samples which do not belong to prototype P, and then we employ ordinary intent, which is a normalized temperature scale cross entropy, as our and contrastive loss. Then, following this SIM-CLR, we use a projection head that maps the extracted representations to the space where contrastive loss is applied. We use this similarity, which is just a dot product between L2 normalized U and V, which is cosine similarity, and then the contrastive loss of a sample can be obtained. Z is the set of representation in the projection space. But the final contrastive loss should be computed as a sum reduced across all samples, not just one sample. You should compute it across all samples. So even for loss for the metric, we observe that the prototypical cross-entropy employment does not improve the performance of the downstream task. One reason is that the clusters of prototypes are not well separated. So with a projection head that predicts the distance between the pairs, siamese style metric loss could be obtained. And then, motivated by this paper, we introduce a prototypical cross-entropy loss to guide the views of one sample to its corresponding prototype. This loss term is helpful when similarity between the views is small. So the prototypical cross-entropy loss is computed, where G is just a linear projection that maps the representation to the label. So finally, we add all of these contrastive laws and metric laws and prototypical laws. Of course, we use these hyperparameters